the cloud. And now, for something very different but yet familiar.
Yes, today I'm presenting this paper, which is called An Evaluation of Anomaly Detection, Diagnosis and Multivariate Time Series. So obviously all of us work with multivariate time series data. So I thought it would be kind of interesting to kind of see like a comparison of a few different ways to go about anomaly detection. And I'll kind of get into what that is. Although they were not necessarily using like neuroimaging data here, but still was pretty interesting to kind of see. So does anybody have an idea of what like anomaly detection means? Any ideas or thoughts? Okay, well, excuse me.
I could say, so it's, you see it a lot in industrial applications, right, where you have like a sensor or something, like, I've seen it in trains for some reason, they have a lot of times, so they have like a sensor on the train, like measuring like engine speed, normal engine behavior, and so they create a model of normal behavior for this component, be it an engine or valve or whatever, and they're trying to detect like anomalous behavior, right, so the valve is releasing more than it should or not releasing like it should. So it's detecting, like you build a normative model and try to detect deviations away from that typically is how anomaly detection is done.
Yeah.
In my master's thesis, we modeled the epilepsy prediction as anomaly detection, but in the future.
That's cool.
And it seems like most of the, I kind of get the impression that a lot of these disease states that pervade neuroimaging could be considered a form of anomaly detection because we don't have tons of positive examples for this thing.
Yeah. Yep, that makes sense. So yeah, basically, it's also called like outlier detection or sometimes called novelty detection. But the major goal is to just kind of identify rare items or anomalous items in these time series data that is deviating significantly from like what would be considered normal or healthy data, or even just the majority of the data. So some of the categories of anomaly detection, obviously we have like supervised anomaly detection, which requires a lot of labels, labeling the data as normal or abnormal. And kind of like, as William said, especially from like a medical imaging standpoint, we don't always have a lot of labeled data, especially for like abnormal behavior. So that's why a lot of the times maybe supervised anomaly detection can be somewhat problematic or having a con. So then we get into kind of like a supervised anomaly detection category, which is basically just assuming that some portion of the data is labeled. And from there, you can just kind of train a model on part of the labeled data and do this anomaly scoring, which I'll kind of explain a little bit more later on. And typically this is kind of done, I don't know if you guys have heard of kind of like semi-supervised clustering and stuff like that. And also it's done like with deep learning and things. But the similar approaches are kind of taken here for the anomaly detection in the semi-supervised case. And then we get into, I guess, like the most interesting case, which is unsupervised. So this is assuming that none of the data has any labels, and that the majority of the data is kind of like from the normal or healthy standpoint. And so typically how this has to work is that some kind of a model has to be created, kind of like Brad was explaining, we need to be able to model the data in a healthy case. And so then how this process typically works is there's this anomaly scoring, and then it goes into the thresholding and then classification. So basically from the machine learning perspective, anomaly detection is kind of done using some kind of a classifier or other kind of predictive model. And from there, it's just kind of the models used to identify outliers or rare events in data sets. So these kinds of models obviously can be trained to classify whether a given data point is normal or abnormal, so it's usually like a binary classification. And from here, they kind of just learn to identify anomalies based on deviations from the learned data. So some of these techniques can include like clustering, density estimation, etc. So I kind of just wanted to look into this from like the neuroscience perspective to kind of see like what was out there, what kind of has been done already. So typically how this works in neuroscience research is that it's applied to neural data. As we know, neural data is captured with respect to time. So it's high dimensional, it's varying with respect to time. And so basically how this anomaly detection works in neuroscience is it's used to kind of identify unusual brain activity. And again, it's kind of subjective how you define unusual brain activity, but this detection could be used to kind of find some kind of biomarkers or basically just try to find some kind of an indication of like a neurological disorder or some kind of an abnormal neural response, specifically in like task-based studies and things like that. So these are some example applications that I found. So one paper, they were kind of looking at the interaction between brain networks, which is what we typically do. We usually look at like interaction between brain networks, using the like correlation between the networks. So this paper was kind of looking at changes over time in brain regions as like a graph. That changed over time. And then another paper is this reconstructing time series. So basically what they did was they would take in a time series of brain data and use an autoencoder to try to like reconstruct the time series data. And then they would look at time points that had like a high reconstruction error and then kind of like threshold that to determine like if someone had like schizophrenia, or kind of just looking at those reconstruction areas, those regions with high reconstruction error. And they were kind of able to find like specific biomarkers that were biologically significant. So that was kind of a cool paper. But yeah, that's typically how I think it's been done so far in neuroscience research. And then there's a nice review as well. So
An
basically,
interesting thing I observed on the epilepsy stuff is that, and my mentor observed is that basically everybody's got anomalies in their data, but the people who have disease states tend to have like a longer, more persistent anomalies than everybody else. So it's like you can combine like an unsupervised thing that can kind of like observe the anomalies with some sort of thresholding, and I'm like, how frequent they need to be for it to trigger. It's supervised.
that kind of makes sense. Like, so epilepsy is kind of characterized by seizures, right?
Yeah, it's
Okay.
like a
So they're kind of looking for spikes or something.
pre-ictal state is the pre-seizure state that where you should begin to start looking at anomalies. And the ictal state is the seizure.
Yeah, I think people have been looking at like fMRI here and also like EEG and stuff, kind of looking for spikes as well as like, just biomarkers and stuff.
Yeah, the standard, at least from a couple of my colleagues were working with epilepsy data in Barcelona, and then they actually were working with a clinic that specialized in epilepsy. So you have people sitting in hospital for a couple of weeks with probes in their head. And there's typically, there's a pre-seizure stage that if it reaches a certain critical mass, will generate a seizure.
Yeah.
And mostly they're looking at EEG. Mostly they look at EEG data for that.
Is that kind of because like EEG has like a better resolution or?
Much better time resolution.
I think it's also much more data.
It's also the much better time resolution. Also, you can't predict when the seizure is going to happen. So To get an MRI scan, you'd have to have them sitting in the scanner continuously for like a week, which is just not gonna happen. So. For these patients in hospital, these are patients who, you know, they're non-responsive. They're trying pharmaceutical, it's non-responsive. So. These are people who try pharmaceutical interventions, non-responsive, so they're going for a surgical intervention. They will have a microarray of probes implanted in the brain. And
Have like a biological pacemaker for the brain and like that.
no, it's just a sensor,
Okay,
but or several hundred sensors, really.
yeah.
Or they'll then be sitting in hospital waiting for a seizure to occur because typically epilepsy patients, the seizure will start in a very specific part of the brain and then radiate out from there. So the sensor array is there to detect when that occurs and where it occurs. That's why they need several hundred of them, so
Yeah.
that they can detect, okay, these. It begins at this channel.
Mhm.
You know, EEG, you have a lot of muscle-like artifacts and eye-link artifacts that you have to filter out, and then with the implanted array of electrodes, you don't have to deal with as many artifacts, and you have higher resolution.
So. Yeah, so clinically, what all this is for is so the surgeons can identify which region of the brain is causing the seizure and then plan an operation to remove it, assuming it's not doing anything vital. As far as research goes, it's actually something of a gold mine, that you say you can get all this data without any of the, at much better spatial resolution. EEG level time resolution, but much better spatial resolution and without all these artifacts.
Oh, and what modality is that? You're saying like as an
Micro-
alternative to EEG?
Yeah, then, so like. the whole-
Microarrays, implanted microarrays, so like think EEG, but directly on the brain surface instead of on the scalp.
Oh, yeah.
Yeah, there's like, I mean, I actually did a presentation, Ashcon about like all the different types of electrodes that you can use, but, there's these like polymers that basically are like go on the top of the cortex and they can get spatial resolution along the cortical surface without too much invasiveness. And then there's like these, I forget what they're called, but they're like, they're long and pointy and they actually just like go deep into the brain.
Yeah.
And they have like, electrodes along the spike. So, but that's all invasive stuff. So if you have to, the next alternative was like optogenetics, which is like viral targeting of nerve cells, and then you can get a light source that will like be on like the outer part of the cortex that will respond to any photons that would emitted by neurons that are like has gene alterations. So that's like but the arc of how you can interface with the brain to get the same.
What type of virus do they use, like adenovirus or what?
I think you can use adenoviruses, but I remember they talk about herpes viruses and stuff like this. There's a bunch of different viruses that they can use, and then there's gene altered mice and stuff. But and then theoretically that would mean you'd have to get like gene therapy as a human early in life to get that sort of stuff.
The typical clinical array situation is one of the two he was describing earlier. It's either on-brain network or these microarrays of probes, so very thin electrodes that are actually inserted into the tissue. And as I said, it's highly invasive, so it's only, this is why it's done for patients who need an operation. They've already tried every other intervention. It's the last option.
One of the operations they do is like removing like a whole hemisphere. It's crazy, like the person's actually kind of remains semi like themselves, but they like a hemisphere.
task 12 though, because within your hysterectomy, like, the pre-12, so it's still,
People out working with one doing anything that from.
It's like if you basically have like a near fatal.
Try to go for much more precise intervention than that these days.
The ultimate goal of the non-invasive techniques though was because clearly everybody's worried about risk of invasiveness. And so like a lot of the seizure patients will fall during their seizure and hurt themselves, so they need to be forewarned in advance. And there's now there's like these things that you can kind of put on your scalp and walk around with and collect that data in real time. So the idea was to have like a device they could wear at one.
Wow, that's nice. Yeah, I think they had some talks about like the deep implants that were pretty fascinating. I think they were in the brain space group a while ago. But yes, so that's kind of some of the work that's being done, at least in terms of like fMRI. It's pretty easy to just kind of use something like an autoencoder and kind of like analyze a reconstruction error in different, regions of the brain and kind of look for biological significance. But the data that they were using here, kind of like what Brad was sitting on, this is mainly looked at for like technology sensors like aircraft and servers. So basically they're using these cyber physical systems sensor data. So it's obviously multivariate time series data, and they just collect it from these sensors. Like maybe like for a server, you might be monitoring different hardware points, and similarly with aircraft and other manufacturing systems. But they mainly focus on two things here, which is anomaly detection and anomaly diagnosis. So for the anomaly detection part, they're basically trying to identify whether any given time point from a sensor is anomalous or healthy. And then for the anomaly diagnosis, they're trying to pinpoint like which specific channel or sensor is anomalous or unhealthy. So we'll kind of like get into what they do with that. But one is on like the time point scale. Another one is on the event scale, or you might say the sensor scale. So their main research objective was to try to like characterize some key design choices that's being done with these deep learning based multivariate time series anomaly detection tasks. They're just kind of trying to kind of analyze why are people designing their models in this way, and what impact is it having on the results and performance. And they kind of pick apart different design choices and kind of mix and match them with different models to kind of see how it affects the performance as well. And they also use, again, this real life cyber physical system data. So some of the key questions that they pose is kind of something that I already kind of explained a little bit, but they want to know what is an appropriate scoring function to use for anomaly detection and analysis. I'll kind of explain what that is a little bit later on. Another question that they ask is like, how important is the choice of scoring function compared to the choice of model for good performance? And they kind of look at some existing algorithms that are popular in the field for anomaly detection and kind of see how well in general they perform on some of this cyber physical sensor systems. So this is some of the models that they kind of look at. There's a lot of different models that they were kind of comparing here, so I won't go in detail about everything that was used, but they looked at feature learning methods. So, for example, an autoencoder is a feature learning method. So they looked at a variety of different kinds of autoencoders. Another feature learning method is the GAN, generative adversarial network. And they also looked at predictability modeling, which I'm not super like familiar with what that is. And then they also looked at anomaly measure dependent features. So basically, it tries to learn features for anomaly measurement. Then they also looked at these different end-to-end scoring techniques. So one of them is a method for scoring anomalies. Another one is kind of like a different one, which is more comprehensive. And finally, they looked at some shallow techniques that we're all kind of aware of, which is PCA and SQs. So this is the basic problem setup. So for the anomaly detection. So given a training data set, so they have just basically a bunch of time points. They have a bunch of data points. Each data point has a number of time points. And each data point as well has a number of channels. So we can kind of think about this as like time series data for us. Our channels would be brain regions, and our time points would just be the number of time points in the fMRI recording. And then, but what they do is they kind of like sample a subset of the time points to be used. They don't just take the entire record of time points. But they do like a regular sampling, so they don't do any kind of irregular or random sampling. So for the test data, they also take just basically a subset of the original time series data. And so for the anomaly detection task, they make a prediction at each time point t, where the time points go from 1 to the last time point in the test data set. And their goal is to find whether an anomaly occurred at a given time point t. So for the anomaly diagnosis problem setup, they're given this training data, which is, just again, like a multivariate time series data. And they also have the test data set. And their goal is to find whether a specific channel deviates from the normal behavior when, compared to the other channels. So these are referred to as causes of the anomaly. So these are some of the data sets that they used. They used a lot of different kinds, like whether it's like natural data coming from like water distribution or water treatment plants. They also looked at like some food manufacturing data, as well as spacecraft and server monitoring data. So yeah, that's all the data sets that they use. I might get into like a little bit more of what, why it's kind of those data kind of important. I can't see my notes, but that's fine. But yeah, so the next thing that they kind of did was kind of generalizing how anomaly detection works in a way that they could kind of tweak different modules of this process. So they kind of generalize it into 3 main parts. The first part being the reconstruction or prediction model. So that's basically a model that just takes input as like a time point or a series of time points and tries to either predict the next time point or a series of time points or reconstruct the next time point or a series of time points. And then there's a scoring function module that they're kind of claiming is like a general part of all anomaly detection tasks. This scoring function we'll kind of explain a little bit more as we go on. But basically it just kind of transforms the reconstruction or prediction errors into some kind of an anomaly score. And then from there, they basically perform this thresholding operation, which is which kind of just leads to the classification of an event or time point as being anomalous or non-anomalous. So just kind of getting into the reconstruction or prediction model, which is their first part kind of this generalization of how anomaly detection works. So basically they just have some kind of a prediction or reconstruction model. This is just denoted as F sub m. But it's essentially a function that takes input and the input is a subsequence of a time series. So they scale it using like, regular, pre-processing techniques. And, the output of this model is basically like a lossy reconstruction or a prediction of the next time point. So, if you kind of think about like an autoencoder, it takes in, the full, dimension, data object X, and then it, through a series of, transformations, kind of compacts it to this latent space. And then from that latent space tries to reconstruct it back to the original input. And so to calculate the error, you just find the difference, between the input and the reconstruction. That's kind of a simple way to think about it. But basically the error is calculated for the time point with respect to each channel. So the result is a matrix, which has all of the time points, with respect to all of their channels. And each entry in this matrix is a value, which represents the error in either reconstruction or prediction of those time points, again, with respect to all of their channels. And,
So
yes.
let me ask a question. So sorry to interrupt you. I wondered what is the function FM? It should be anything, I mean, it could be anything, or it is defined based on some criteria.
Yeah, it just depends on what model you're using. So, if you're using like, an autoencoder, it would be like a series of neural networks that, just compresses the input down to a latent space and then reconstructs it.
So it could be anything, and
Yeah.
the just differences in the process of computing, I mean, training and getting the output. Am I right about it?
Yeah, I think basically, that's kind of why they're using the M subscript, because M is just kind of indicative of which model that you're using. So, yeah, the input will always be the time series data, and the output will either be like a lossy reconstruction or some kind of a prediction.
Be a matrix factorization model, could be anything, like. FBA is a reconstruction model technically.
Yeah,
Technically. In a weird way.
For example, we use SVM instead of FM.
SCM's not really used for this kind of problem. You could use, I guess,
It used to be used about 10 years ago, but
they use an SVM here?
no, I said 10
It
years.
was,
Yeah, they
Sergey
did.
was gesturing at the.
Single class SVM,
Yes,
the anomaly detection.
that's like it's
For
bread and butter.
reconstruction?
No, for
No,
anomaly
for
detection.
anomaly detection.
That's what I was talking about, reconstruction models, yeah.
yeah, I think that's more like the classification part of this problem, but they do, compare, their models with SVMs as well. But yeah, it can just be any model, I think, that can perform this, reconstruction or prediction step, given a series of time points.
Well, something completely off, sorry, but I forgot whether Preston is talking about it, that's an old principle. So like if we have a model that predicts everything and then something is an outlier, something is not being predicted by our model. It's a learning signal for our biological brains. Hey, we need to update the model. It's not that, yeah, just smooth it out.
Right.
Although,
Yeah, this is like a continuous learning issue.
yeah. It's like, oh, the system, the world may have started drifting, right? Like, hey, the volcano is erupting, we better relocate, this little animal moves away or something. Instead of like, just something.
Yeah, any other questions or comments? So yeah, and then we just kind of get into the scoring function of this process. So essentially we have this errors matrix, again, where each entry in this matrix just kind of represents a time points, either error in prediction or error in reconstruction, given all of its channels, or with respect to all of its channels. And so this transformation function, is responsible for converting the raw errors into individual anomaly scores, individual channel anomaly scores. So the input is this channel-wise reconstruction error, again, in the form of this matrix. And the output is this, is a channel-wise anomaly score. So basically, they kind of just convert these scores, these errors into scores. And I think the scores are kind of representative of like how likely it is that a certain time point is anomalous or not. Do you have something? Oh. So the aggregation function is another part of this. So from what I understand, it basically combines all of these channel-wise anomaly scores to a single anomaly score for each time point. So the input is these channel-wise anomaly scores in the form of this matrix A. And then the output is an anomaly score for the time point T. And again, this is across all channels. So kind of just aggregating for a time point across all of its channels, kind of like its score or likelihood in a way of it being an anomalous time point. So after that, the third major part that they're kind of saying is general to all anomaly detection tasks is this thresholding function. Which is responsible for classifying each time point as either anomalous or healthy by its anomaly score. So basically, after we do this step, which is the scoring function from what I can tell, they do this aggregation, which is basically combining it into one single value for each time point in the time series. So then they basically just look at that value for each time point and just apply a threshold. And that threshold just determines whether or not this time point is classified as either anomalous or healthy. So this kind of seems like just like a binary classification task. I'm not sure if this can be done like in a non-binary way, but from what I can tell, it just seems like either anomalous or not. I don't know if there's opportunities for more class labels, but yeah, so it seems like typically the label 1 is applied if it's anomalous, and then the label 0 if it's healthy. And they didn't really explain, like, I guess in detail what this part means, but they're ranking channels for duration of anomaly. So then they rank the top 3 causes, and then they use this part as anomaly diagnosis. So I think what they mean by anomaly diagnosis is basically trying to determine which channels are anomalous, and then they're kind of using these channels as causes. So I guess from a neuroscience standpoint, you can kind of think about like which brain regions are anomalous. That seems a little bit general to me, I guess from a neuroscience standpoint, but
Sorry, say that again.
I'm just saying like the way they're doing this, they're kind of saying like, okay, if overall we're gonna aggregate all the time points anomaly score together into one value, then we're gonna sort all of the time points according to their channel to see like which channels had the highest anomaly score.
Time points or time series?
Time points, like, yeah. So they're gonna sort the channels based on the anomaly score, and then they're gonna take the top channels as causes. So I guess for us, the channels would be like brain
But
region.
basically, you're looking for the channels that have the highest correlation with the anomaly.
Yeah.
That makes sense for stuff like EEG, when an electrode starts drying out or disconnecting and things like that. It's the electrode that's giving you the problem
Oh, yeah, that makes sense.
for stuff like that.
I guess for fMRI, I wouldn't really understand like the impact there, but.
You might, maybe like functional units or whatever they all work with, not the structural, so I don't know the terminology as well, but the
Oh,
like
yeah,
different brain components.
the networks, yeah, I guess, yeah, I guess like if you were to implement this on fMRI channels or, you know, our like neuromark channels per se, you could just kind of see, okay, if these top channels are anomalous, we could take these, see if they have some kind of biological significance.
Right, yeah, that would be kind of causality related, I mean, like trying to get causality out of correlation, but yeah.
So, they kind of did a lot of different, experiments with different models, kind of swapping like the different like scoring, functions that they used, as well as they were kind of looking at different, ways to evaluate, the performance. So, this is just kind of breaking down like some of the different evaluation metrics that they used. I'm not sure if this is something that they came up with, or if it's like widely used, but the composite F score.
Is that F scores?
Yeah, there are different types, one that they looked at was a composite F score, so it's just the harmonic mean of time-wise precision and event-wise recall.
Yeah,
I think that's kind of common use.
The model of evaluations is kind of dependent in a way, so like you need to make the trade-off between like whether you throw up false alerts, but you get more accurate alerts that when they actually happen, or if you just want to like not have false alerts at all.
Mhm.
And so like choosing where you fall on the receiver operating curve is kind of like a trade-off between the true positives and the true negatives, false positives and false negatives. And F score is one of the things that they use to optimize this. So
Yeah, so they're using this composite F score. So it's made up of these two major terms. One is the time-wise precision. And it's kind of denoted as this PRT here. So it's made up of the number of true positive time points and the number of false positive time points. So basically, it's just a measure of precision at the time point level. So this is just a typical formula for precision that we're all kind of familiar with. And then we have the event-wise recall. So this is where they're doing things on the event level. So basically, they're measuring the recall of an event at the event level, which is focusing on entire events. So basically how this works is, they're gonna take the number of true positive events, and they're gonna use also the number of false negative events. And basically, how do you calculate a true positive event? These are events where at least one time point was correctly identified as anomalous. So if you have an event or channel, during which one of the time points was correctly identified as anomalous, then they just consider that entire channel as a true positive. So they also have this false positive, which is the number of negative events. So basically, this is where true events, these are only true events where no time points were identified as anomalous. So, let's see, true events where no time points. Okay, so this is where they did not find any time points that were anomalous, but they also didn't have any false negatives. So they combine those metrics to get this harmonic mean type score, which is below here, which is denoted as FC1. And so they're kind of claiming that this is kind of like the best score that they could come up with, or kind of represent this scenario that they're trying to do.
yeah, I mean, it's just like, you gotta think about what the values can be. The values can be between 0 and 1. So like, if you like wanna maximize something that's multiplying variables that can be between 0 and 1, then like you multiply them. If either is 0, so like if you're kind of like too unbalanced on like where your bias is, if you're basically a heuristic, for example. Then like you'll make the thing 0 by being too unbalanced, but these harmonic means make a nice balance, so like when both are kind of like at 0.5 and multiply them, it's much higher than if either is unbalanced.
Yeah. Yeah, so this is kind of what, one of the ways they were kind of measuring, I think, the performance of some of these models. So these are some of the other metrics that they used. They're using the regular F1 score, which just basically measures the overall performance by balancing precision and recall. So I think one of the cons here is basically it can be like overly pessimistic. So I think it just kind of depends on the like true positives and these formulas here. Another one that they're using is the point adjusted F1 score. I don't know if you guys have heard of this. I think it's sometimes called like the micro or the macro something score. But it accounts for events by treating all time points within an event as true positives if any time point is detected correctly. But one of the cons that they were kind of saying with the score is that it could possibly give overly optimistic results. And then they're also using this composite F1 score, which combines the time-wise precision and event-wise recall, providing a balanced view of detection quality. So they kind of played around with some of these scoring functions that they were using as well. So one scoring function that they used is this normalized error. So basically how this works is it subtracts the channel-wise mean training reconstruction error from test errors, and then it takes the root mean square across channels. And basically the reason for doing this is to normalize errors and account for differences in reconstruction error across channels. Then they used this other kind of scoring function. So this one basically fits a Gaussian distribution to the training errors and uses the cumulative distribution function to calculate anomaly scores. So I'm not exactly sure how these work per se. So this is used to kind of transform these errors to an anomaly score, kind of like a probability of points being anomalous.
What about Laplacian distributions and flat tail distributions and things like that? Those are super. It's interesting. Okay. You know, sometimes you always have outliers, but they're not outliers. It's just distributions. Flat tail.
Yeah, so that is something to think about. They're kind of using these Gaussian distributions. So they're assuming that the data is kind of having a Gaussian distribution. So it's possible that it doesn't, obviously. So it's kind of saying too, they note directly that using the probability distribution function would give points at both tails of the distribution high scores. In particular, this means that even points with very low reconstruction errors will be classified as being anomalous. To avoid this, we instead develop a score based on the cumulative distribution function, which is negative log of 1 minus the cumulative distribution function. So they're saying this increases monotonically with reconstruction error. So they basically have this formula here that they use for this measure. And then they also have this other method that they're using, which is called Gauss-D. So I think this is some kind of like a dynamic measure or a way to kind of fit these errors to these scores for anomalies. So they're using this dynamic mean and variance, which is based on a moving window to adapt to long-term changes during testing. So basically they update the mean and variance with a window size that adapts to better handle variations during the test phase. The last kind of Gaussian scoring function that they're using is this Gauss-D-K. So it applies this dynamic Gaussian kernel convolution to smooth scores and kind of amplify the total anomaly scores. They have this formula here, which kind of explains. So they're using a convolution to aggregate the scores across channels, which kind of makes sense. And the purpose is to enhance detection by combining responses from multiple channels and smoothing the scores. So this is kind of their experimental setup. They just kind of did this normalization. For the training data set, they did a channel-wise min-max normalization between 0 and 1. And then they did this clipping to range -4 to 5 to handle large values. And so then they also set these window parameters. So the window length, I think they set for 100 time points and then 30 time points for high dimensional data sets. And then they did the step size 1 for shorter data sets and 10 for longer data sets. So they did also they also did some setting of these hyperparameters and for these other models that they're doing here for the LSTM variational autoencoder and some of these other. So the method that they used for the hyperparameter search was random search, and they selected these based on the minimum reconstruction error. And so these, as far as the scoring function goes, this W factor, which was mentioned in some of these other formulas here. They were kind of just setting this right relative to the training set size. Because I think this is kind of controlling the scoring function context within the time series window. So I think maybe like the larger data sets would need like maybe a smaller context. So then they also set this sigma parameter, which empirically sets, was again empirically set for each data set, and just kind of varied by data set. And this parameter controls kind of the scale of the anomaly score and the scoring functions. So as far as the experimental setup goes, the evaluation, the primary metric that they were looking at was the F1, the composite F1 score. And again, they kind of compared this with other metrics. They also kind of looked at the ROC, AU ROC and AU PRC scores. And they did 5 runs with different speeds, averages were, and their averages were reported. And they also did statistical significance testing at significance 0.05. So this is kind of a graphic of some of their results. So this is kind of them looking at different scoring functions. It's kind of hard to see, but so you can kind of see like along the x-axis is the different scoring functions that they use. So there's the normalized error, the Gauss S, Gauss B, and the Gauss DK. And then they looked at the different data sets. So kind of each data set was having like different kind of performance. I guess because of like the nature of the data and things like that. But they're kind of saying for these data sets, the DMDS, I'm trying to remember which data sets these were. I don't know if these were like natural data sets or something. Let's see. Okay. Yeah, so I think for these data sets, DMDS, SMD, SWAT, and SCAB, these came from like, I think, factories. So it looks like the choice of scoring function significantly impacted the performance more so than the choice of the model. And then they were also looking at the dynamic scoring functions like the Gauss DK. And they also were kind of saying that this performed pretty well. But they were kind of saying the best scoring function that they used was the Gauss DK. It was kind of outperforming the other ones and as well as the Gauss D. So it looks like the Gauss DK was the best at handling anomalies across channels. So that's pretty much it, I think, for today. I think we're kind of running out of time, but basically what they did was they just kind of tested a lot of these different models, kind of playing with different scoring functions and thresholding and things like that. And it was kind of interesting to see the way that they kind of generalize and explain the anomaly detection task. But it says that some of their future directions would be maybe like model improvement, enhancing some of their models with advanced techniques, and kind of looking at more complex data sets with maybe like more diverse conditions, better evaluation. Yeah, any other comments or questions?
I'll say this, I mean, anomaly detection is sort of like a first go-to when you don't have a lot of good data for the thing that you're actually interested in, but there's like it's a huge handicap to not have that data, because whatever you're modeling is normal will have some anomalies in it. And like that, having those other labels to know what part of your decision boundary needs to be carved out of that normal data is absent. So that's the big problem with like one class SVM. Like any sort of anomaly detection that doesn't use supervision, you can never achieve quite the accuracy that you'd like as you can with supervision.
Mm-hmm.
But you have lots more normal data than
Right.
anything else, so it may be still a good choice to start with.
Yeah. It's really
Healthy, non-healthy.
It's
like,
really
I don't
hard.
care if it's schizophrenia or which type of dementia, it's just, if you tell me this is not healthy, I know what to do next. It's like now you go to a specialist,
Mhm.
we do that.
Yeah, and there's one really cool thing that came out of like the nonlinear dynamical system literature, which is like kind of where you like drift to if you wanted to go like further into your studies in anomaly detection. Like basically like in any nonlinear dynamical system, the like components are coupled in some way, so there's like correlations between like the activity in one component of the system and other components of the system.
Mhm.
And you can detect anomalies, say, in the brain by monitoring things like heart activity, sweats, gaits, things like, and other things like this. So, and that translates into other things like earthquake detection and like, like it's such a generic concept, like you were showing in some of the data sets that are non, brain related, that it's,
Yeah.
a powerful tool.
Mm.
I do have a question though. Does it tell why that time point is an anomaly? Like, is it because of frequency or just amplitude change? Does it have anything with regards to that?
Just amplitude, I think, right? They're
Does
not
that-
doing any, they don't do any wavelet transform or FTs or anything on this data usually.
So it's just like
Yeah,
a spike.
Just amplitude,
Yeah.
usually. Sometimes some of those models will do frequency transforms and also do a frequency analysis, but I don't think any of the stuff you talked about is doing that.
yeah, no. Yeah, I think it is mainly just kind of looking for spikes, but.
For EEG, it would make sense to do frequency analysis. It's kind of weird that they
Yeah.
don't,
Yeah, any other questions?
No, I guess. Thanks, John, very interesting. And not something we talk about often. Maybe it's first time came up since you're here, William, right?
Yeah, I mean, it's like, I'm surprised nobody's talked about EEG the whole time I was here or anything.
Thanks everyone for listening and see you next week with a different topic.